Hello, I am Koyano from the Open Redstone server, and OR stands for Open Redstone Engineers, where we make a bunch of computational systems in Redstone. So this here is the processor. You can find some adders, some arithmetic logic units, barrel shifters, calculators, screens, memory, anything really, and everything in Redstone. Now usually I don't make videos, but I got a lot of stuff to show, and people really pressured me into doing some videos, so there you go. They know I got a bigger processor unit than this one, but this is the first iteration, and was kind of a stepping stone really. This here is KPU1, and it stands for Koyano's processing unit. Yeah, I know, it's not very original, but I don't care. Originally it was meant for survival, and you can see that's not really doable anymore, but the idea of simplicity still stuck around. Like when things get too complicated, you just try to replan, but don't build. And that kind of worked. Like a lot of times people want things to be too complex, or they want the speed to be a little bit higher, and they have to rebuild. It takes too long time. Like big projects tend to not get finished, and I find it kind of sad. Like in the end, it's all just a bunch of simple modules that work together to do something more complicated. So yeah, you may find that the design is quite like Penny Cube's design. Well, we are still OR, like we can share designs, and usually I tend to make my own. But the ALU is definitely mine, and well, memory is taken from Depot. That's a shared unit plot where everybody can build edit in and out, copy designs into their own plots. Also, the instruction memory is mine, and the rest really is just common. So what is special about this one? Well, it's a 6-tick clock processor, but it had to be pipelined to do that. So that doesn't mean that it can fetch a instruction and execute it, write it back in 6 ticks. No, it can handle a throughput of one instruction every 6 ticks. So the PROM handles a new instruction every 6 ticks. I decode every new instruction in 6 ticks. I execute them in 6 ticks, and I write them back in 6 ticks. So it all goes on a conveyor belt. Does mean that instruction pipelining is not as easy as data pipelining. Like there are dependencies within the data loop itself. Data depends on one another between different instructions or branching. Like you mess with the control flow of the processor, so you have to make sure that the whole program stays relevant, doesn't have data errors. Now you can see that my program memory is kind of different from others you see on the internet. That's because it's rewritable. So it's not torch ROM, where you can place torches to get a different instruction. No, you have to load them in from a outside source. For people that don't know what torch ROM looks like, here I have a small example where each line would just correspond with a instruction, and the torches represent what data is on that instruction. So when the line goes up, it just reads them out. Now, the problem with that is, if you want a massive software system, writing your own programs from a keyboard, you need a software design, not where you have to manually place torches. Also, torch from, if it gets too big, it gets slow, really slow. So it might have to hold a program editor, but if you're not using that program editor, it just slows you down. So what you would want is rewritable memory that just executes part of the code that you're running right now and do it quickly. So that's the idea behind rewritable program memory. Now it does mean that it's not as dense. So you really have to think about how efficient are my instructions. This one here has a 5-bit address, and so it has 32 bytes. And each instruction is 1 byte. So 32 instructions, each of 8 bits. So the upper 5 bits tell the opcode the processor is doing. So what kind of operation I want to perform. It can be addition, it can be a jump, it can be a load or store instruction. They were all decoded further into control lines. So things the ALU understands and all the other components. Like, they don't understand the opcodes, they only understand single signals. So things like invert A, or this is something specific to carry cancel adders, B, carry in, like those are all ALU control lines. Yellow is more for data flow. If I want to use an immediate, conditionally, or force it. Carry flag, if I want to write to the carry out flag, the 0 flag, or the master write enable. So compare instruction would just do A minus B, but it wouldn't really write back the result. So in that case, you don't really have to write back to the registers. You only want to update the flags, so you have that choice. So those were the upper 5 bits of the instruction. The lower 3 tell what kind of register I want to use for. So the A side holds the accumulator, so the accumulator is usually the ALU output, the last known ALU output, and I do that operation with a certain register. Now, I did say here that I can use an immediate, so a constant value that never changes and is contained in instruction ROM, so I don't have to use my RAM. Well, it would read a instruction, tell it to want to use an immediate the next cycle, and then the next byte that comes from the instruction memory will be treated as an immediate instead of a register value. Yeah, it does cost you 2 bytes, but there's no other way to do that. Now, onto the execute stage, and that's where the ALU comes in. So it has all the other simple functions like adding or subtracting, but also logic functions like OR, NOR, XOR, XNOR, and NAND. All the implies, nimplies. It even has right shift, signed right shift, left shift. Usually you can do left shift just by adding the same value, but I don't have that kind of architecture to implement that. So it just has a dedicated left shifter. And that's it for the ALU. Now, the data memory, you can either access it by a absolute address or a address from the register file, and that is called a pointer. It cannot point to itself, it can only point to the data memory, but that allows you to do things like going through an array, storing messages, doing data sorting, that kind of stuff. And it also had a port system. Sorry, this was a complete system, but I wasn't very pleased with it in the end. So there were a lot of other devices trying to interact with the port system, and it got really messy. So what it would do is freeze the processor and ask for a device to either send or receive data. And because it is frozen, the device has all the time to either send or receive the data. So if you have a keyboard attached, it just waits for you to enter a key press, and it would send a key press back. Or if you want to reload instruction memory, you would ask storage to fetch you that new block of data. And because it's frozen, it just doesn't want to access any new instructions. So you can see how really handy that is. A lot of processors don't have that barrier of trying to get data from and to the processor. Well, it's kind of very safe as well. Now, this here is just the processor, and with the processor alone, it just manipulates data. Like, do you see any kind of keyboard right now or a display? No, it just manipulates data. That's its only job. Like, it might be limited in the hardware, but if you want to run code, this is the part that does that. So I had storage, I had a screen, I had a keyboard, all hooked up, but I destroyed it. Do you know why? The instruction memory was too small. Yes. I let the user, I had to clear the screen, write what kind of page do you want to run. The user inputs a key press for the page that he wants, and it would run that new page, but that alone costs me 32 bytes. Yes. So for just a simple task, it just had to reload the instruction memory too quickly with something new. You can't really keep that up. Just writing programs, you would have to go around that limit every time. So I found that it was kind of crucial to have more instruction memory to be able to go to the next iteration of KPU. So yeah, that's it for today. When I get to the bigger processor, a lot of the layout will be the same, but I have a spreadsheet for that. So yeah, I see you guys next time, and let me end this video.